and the angle between distance r and the object and the force F is theta. So about this pivot point, if we apply force like that, the this rod, say this rod is AB, say the rod AB rotates about pivot point A, um, counterclockwise due to the force F. Okay, so the torque that gives the effect, turning effect of the force, is defined as R times F and sine theta. This tau is the symbol for torque. Torque about pivot point. Okay. The equation tau equals RF sine theta can also be written as tau equals RF sine theta can also be written as equals R perpendicular times F. Okay. In this case, R perpendicular represents R sine theta, R sine theta in this case. So clearly you can see the unit of torque is a Newton meter. Okay. Let's consider a few examples here. In this figure A, we can find the torque equals R, this distance given here is R, and the magnitude of force is F, and this angle is perpendicular 90 degree, so sine 90, so that equals R times F. Okay, so clearly this force is about this pivot point. This is our pivot point, so it is counterclockwise due to the force F. Okay, let's consider another example here. In this case, in this example, the magnitude of force F prime is less than F, but still the distance is R as above. This is the pivot point. Okay, so you can find the torque, say this tau 2 equals R times F prime sine theta. Again, theta is the perpendicular 90. Sine 90 is 1, so tau 2 is equals R F prime. Okay, so clearly tau 2 is less than tau 1. From this picture, we can see that the torque is counterclockwise about this pivot point. Let's go to the example C. In this case, force is the same, but this time that distance is comparatively less. So we call it R prime F sine 90 degree. This angle is 90. So tau 3 will be R times F. So this tau 3 is less than tau 1 because R prime, that distance is less than R. In example D, torque will be R times F because we are writing just the magnitude sine 90. That gives us R times F. So tau 4 is equals to R times F, but this time this torque is clockwise. So in general, in most of the situation, we write clockwise torque as a negative and the counterclockwise torque as positive. So we can write tau 4 is equal to negative R times F. Okay. In this example E, look at here. This is the pivot point about which this rod will move. So as shown in the figure, this angle theta is the angle between vector R and vector F. So this angle theta here is the angle between R, vector R and vector F. Okay. So you can write the torque in this situation, say tau 5 equals R times magnitude of force F and sine theta. So be careful that this time the angle is not perpendicular. Okay, so just remains theta. So be careful that here this vector R, okay, represented by this line R, and vector force is applied in this way. So from this picture, we can say that this torque is counterclockwise. Okay. The another example given here, the same rod and the same like the pivot point, but in this case, vector R and vector F are parallel to each other, right? If parallel, angle is 0 in this situation. So you can write torque 6 in this case will be the product of R times F sine 0. So that gives us tau 6 is equal to 0. So from this example, we understand that any force passing through pivot point will not produce rotational effect on an object, because in that case torque will be 0. We can use this concept a lot when we are solving the problems. Next, go to static equilibrium. An object is said to be in static equilibrium when the net force acting on the object is 0. So that means you can write net external force we can write summation F it should be 0. Sometimes it's just a matter of symbol. Delta F, summation F is same as we use F net. It's just a matter of symbol, okay? This can be written as, this can be written as total force along x-axis is 0. So net force along x-axis and net force along y-axis is also 0. Okay, net force along y-axis is also 0. Net force along y-axis. These are just a matter symbol in our textbook. Summation fx is written as net fx, and this symbol summation fy is written as net fy. Okay. And the next condition you can write net torque about a point should be 0. So total torque should be 0. So these are the conditions to be fulfilled if the object is at static equilibrium. Okay. Let's use this concept for an example. This is an example of static equilibrium. So let's define the forces acting on these acting on this system. So the forces acting on here from the figure is W1. Other force is force exerted by pivot. And W2, force exerted by the child of mass M2 on the seesaw. And if this seesaw has mass, it also acts, if this is the center of gravity, one weight is W. Okay, this is the W. So these are the external forces acting on seesaw. Okay. If I choose my coordinate system up positive and down negative, say this is my y-axis. In this example, all the forces are along y-axis. So the equilibrium condition demands that total force along y-axis should be 0. Okay. This is one of the condition. Based on this picture, I can write W1 is vertically down, so I will write minus plus FP plus, minus W minus W2. That equals 0. Right? So we got this from using this condition. Next, let's use the concept of torque. Okay. Let's we have to analyze the total torque exerted by each force. Okay, so let's consider each force one by one. Okay, so just consider force like W1. So torque due to W1 will be R1 times W1 sine 90 degree. This angle is here. So it's clearly R1 W1. From this picture, we can say that this is this is the this is the this is the counterclockwise torque. So that's the reason this is plus. Okay. Let's find the torque due to weight, second weight. This is the weight, second weight, W2. So tau 2, we can write R2 times W2 sine 90 degree. But this time, this torque will be negative because you can see here, this will produce the clockwise torque, right? So we can write tau 2 equals negative R2 W2. Okay, so you have to reconsider these steps. Okay, let's see the torque due to force Fp. So I call it tau P. If I use the same concept as above, equation is Fp sine theta. In this case, this R is nearly 0 because this force passes through in this case, the force Fp passes through pivot point. If it passes through pivot point, R is equal to 0, so torque due to the force Fp will be 0. Same, this reasoning will apply for the force due to the weight of this seesaw. So torque due to weight W will also be 0. Okay. Now we can use the concept of equilibrium. One of the requirement is total torque will be equal to 0. So this is the total torque about the pivot point. So we can write tau 1 plus tau 2 plus tau P plus tau W. Okay, that should be 0. So tau 1 will be replaced by R1 W1. Tau 2 will be replaced by negative R2 W2, and rest, these two terms will be 0. So we can write R1 W1 negative R2 W2 equal 0. That gives us R1 W1, this is the weight, equals R2 W2, this is the weight. Okay, that's how we use the concept. Based on that, you can practice this problem. Say, for example, in this problem, say this is my x-axis and y-axis. Say for the point A, that distance will be r. This is the perpendicular distance from the pivot point. So your r for the force F for the force A will be this 0.12. This is your r. So you can find the torque due to force A will be r times force applied at the point A, which is Fa. I write that, and sine 90. In our scenario, you can look at that. The right? So our R is 0.12. Your FA they give you is 40. They give you this number as 40. Sine 90 is 1. So we can write 4.8 Newton meter. But be careful that this will be minus because the torque due to this force will be clockwise. Clockwise torque, that's why it's minus. So you can similarly do find the torque because of these forces and answer all these questions B, C. Okay. Similarly, practice 2. And here you will explain with example. And third one is also a multiple choice, but explain your choice.